welcome back. Today we're gonna finally finish up local variables. We've done this in like three or four iterations of slowly fixing things, but today we're gonna do it. So in the last lecture, we finally added the functionality to use function arguments instead of just declaring them. The issue is that you couldn't assign to them. And so that meant that we could do stuff like recursion. So we're still Turing complete at that point, or maybe not Turing complete. There's no infinite arrays yet, but we were pretty complete. But we still couldn't do kind of iterative things like this factorial implementation. And so, just a general overview of the issue. So LLVM gave us function headers with parameters for free. We didn't have to do anything special for that. But the issue is that those parameters were virtual registers, and we know that those are immutable. So we can't overwrite them, we can't store data into them, they're just what they are. And so if we compiled this program with our compiler, it would print out 5, even though we would want to print out 10 according to what C should do. But it's not an unsolvable problem, and in fact, it has a very comfortable solution. Whenever we generate the function preamble, we are also going to generate allocation and store statements that immediately copy the data from those virtual registers into stack pointers. So if we've got function Bob with 2 integer inputs, x and y, then when we declare, I changed back to having these be numbers, but the actual spaces for variables on the stack, we're going to give them the names, and we'll allocate space, and then we will store the thing that got passed in immediately into it. So now %x is an int pointer that points to the value of x, and the same thing with y. And while we are doing the function parameter fix, it does make sense to add support for non-global variables as well. We can't do scoping just yet, so you can't have multiple int x declarations per function. And that's just due to how we've structured the relationship between the parser and the generator. But at least for now, we're going to have variables that are local to their respective functions. So you won't have any int x's in different functions that are colliding with each other. And so the meat of the solution is in LLVM function preamble. So let me just go to the file. All right. So the first thing you'll notice is that so let me just go back down to the diff function preamble. First thing you'll notice is that initially we would, when we're declaring the function, we would give the parameters the names that those arguments are tied to. But now we want to give them numbers, because those names I feel like should be used for when we're actually interacting with that data, right? Instead of just at the function header. And so that's just a quick little change. One thing to note is that if you're doing this, then the virtual registers have to start at 0. They technically always start at 0, but it just gets hidden by the function declaration, which I believe takes up a local virtual register. And so, but that's nothing crazy. That's not anything we can't do reasonably. The big change comes here. So initially we just had this loop that would build a list of LVM values to return at the end of the function. But now what we're going to be doing is we are going to immediately allocate space on the stack for our variables. And then once we do that, we are going to call this function store local. In the last lecture, when we wrote store local, it was really simple. It was a one-liner. We would just take in an LVM value, and then we would we would take in a global symbol table entry, or a symbol table entry, and we would update its latest LVM value. That's not going to work because we don't want to tie the virtual registers that we got from the parameters list as the latest values. We want to store the pointers to those so that we can overwrite them and whatnot. And so I've updated store local, and we'll look at that in a second. And we'll look at it now. But the general idea is that now we can also pass in LVM values in addition to symbol table entries. And so, yeah, let's see how that is doing it. So definitely upped in complexity. It used to just be this line right here. But now we're going to say if the input, if the thing that we're storing into, if it's an LVM value, or it's a symbol table and whatever we're assigning to is a constant, because that was a bug that I didn't realize in the last one. Because, imagine we just have this line in the last lecture. If our value is a constant, constants don't get generated anywhere. So this could potentially cause bugs in other places. So we want to store them like we would normally. But what we're concerned about in this case is if type var equals a LVM value. So this says store something that I have into an LVM value. We are going to ensure that we have a reference to an LVM value just by grabbing the latest value from a symbol table entry if we have one. We're going to ensure that everything is loaded properly. So our value, if we have int x equals 5, that x is now going to be an int pointer, right, that we want to store into. And so we want to make sure that if lvar, the left thing that we're assigning to, if its pointer depth is 1, then the right value should have pointer depth 0, right? Because that our store instruction requires that the thing on the left be 1 less than the thing on the right. And we're also going to resize just to make sure. I realized there need to be a few more calls to these around this entire file. So there were a couple bugs I caught today. But yeah, just resizing to make sure that whatever we're sticking into the left variable is the same number type as it. And then, so store statement, nothing like what we haven't seen before. Except the thing we're storing into is a register, as you can see right here. And at this point, we have so many store operations somewhere in that range that I started labeling them for debugging with comments because it was getting kind of ridiculous. So anyways, but believe it or not, that is really the only thing that we have to do to get function arguments working. You do have to update some other places so that it knows to treat local variables as pointers instead of values like it did before. But it's not that bad. The bad part is generalizing this. I say bad, just more complicated. The more complicated part is generalizing this to local variables as a whole. And hopefully you should be able to see how what we just did should generalize to declaring and whatnot. Didn't finish the slides. I'll push the finished ones sometime soon. But the first thing that I've changed to add support for local variables is I've made this new token type called var_decl, variable declaration. And this is our declaration statement parser. And where we used to declare a global, which, if you'll remember, would write some text to an external file, and then after the compilation, it would merge it back in. Now what we're going to do is we're just going to return a new AST node. And the reason we can't just do a declare local the way we would have done a declare global is technically in the past couple lectures, we could have declared globals inside of the main file because of the way we restructured the parser generator relationship. So that would mean that if we declared locals right here, they would pop up outside of the function declaration, which we don't want. So we need to we need to make sure that we're only generating code for declarations inside of the function once we've started the generation. And so this is inside of the AST to LVM function. If we've got a variable declaration, get its symbol table entry, and then let's declare a local. Which can you guess how we're going to do that?
Declare a local?
Yeah. What code would we generate to declare a local variable?
Maybe like a stack allocation.
Exactly. So creating an LVM value, doing stack allocation, increasing that pointer depth by 1. That's just to make sure that the stack allocation doesn't think we're going one further than we should. If we're trying to allocate for an int with no pointer depth, we want to allocate for an int, but we've actually just allocated an int pointer, so we're bumping up the pointer depth right here. And then if we want to give it some value by default, which we don't support yet, but we will eventually, then we'll just store a local. But really, the only code right there is a stack allocation. So that's nice. That wasn't too complicated. So that does have one interesting ramification. So because of the way that we're treating local variables like this, with this pointer depth that's secretly one higher than how we want to treat things, whenever we dereference stuff, we actually have to dereference it twice, which is a little weird. But consider that if I have an int pointer pointing to some value, and it's a local variable, it's going to be an int pointer on the stack. And so if we want to dereference the int pointer, we actually have to dereference it twice to get rid of that abstraction level of pointer depth that we have. And be careful here, because I forgot that LVM dereference gets called. Oh, I thought it did get called somewhere else. Okay, well, maybe those. Oh, stored dereference had something. I guess not. I guess it didn't have anything. I don't know. I'm going to write a comprehensive update of all the little bug fixes and what they do, because there's a lot of them, and I don't remember them because I wrote them late last night. But doing everything that we just did, we basically now have support for local variables, and I'll show an example. Alright, branch, good.
So wait, if I'm having issues, like I didn't completely finish the last lecture. Is a lot of that like undone by this lecture, or does it build on top of that?
I would say it does generally build on top, but it might help to have both diffs open at the same time, or maybe just jump straight to this one. I don't know. There is, I think, a fair amount of overlap, but not completely. But that does bring me, before I show you the example, the thing I was working on right before class. I got rid of the print statement. And let me see, grep, LVM preamble. I don't know if it's called LVM preamble. Ugh, I'll just show you in VS Code. So I added a hard-coded.
What does RN mean in grep? I know what R is. What is that?
N gives you the line number.
Oh, that's useful.
Yeah. LVM.py.
Because I was always grepping and then searching in Vim, but that's easier to have the line number.
Yeah. Grep inside of Vim never works for me. I don't know how to use it, I guess, but.
I was grepping outside of Vim. I was grepping outside.
Oh, gotcha. But so anyway, I've declared this function printInt right here, and all it does is it takes in an I32, and it prints out that value, just using what we've, the code we've used before. And it's important to note that you also have to hard code it into the global symbol table, because we don't want to make people, I don't know, we couldn't make programmers implement printInt right now. It's not possible. So we have to hard code this entry in so that the generator thinks that there is a function called printInt that it can call.
So it's kind of like a standard library with like one function.
Exactly. Yes, and we could do more of this. We could write plenty of standard library functions this way, and that would be very interesting. The way that ACWJ does it is they have a standard library that they wrote in C that they link after generating. So the printInt function for ACWJ is written in C and is compiled with GCC or something, and then he uses the linker to be able to call printInt in his generated code, which is a really interesting way of doing it. We could do that, but that's work that I don't want to do yet. Eventually we'll have include statements. I wanted to do the preprocessor today, but I don't think I didn't have enough time last night. But I said I was going to show you examples, test, factorial. Oh. We don't need that warning anymore because both of these work now. I can show you. Scripts, run, examples, test, factorial. We agree that this should print out 120 twice, right? Boom. Let's look at there's our printInt, and here's iterative factorial. So declare local variable x. We're gonna store our first argument into it. we've got this variable y. We're going to subtract 1 from x to get it, and this is where we're checking the loop condition. We're going to load x and y. We're going to multiply them together, and then we're going to store that back into x. Boom. That's great. And again, the reason I changed these from being the variable names to these being the variable names is that we actually use these everywhere, but we only use the parameter instance once. So we can still see x's and y's way down at the bottom, which is great. So that's cool. That's really neat. I like that. Let me see. There's also a test function. Oh, the other thing that this fixed is this works now. Didn't work before. The issue is that we couldn't store. I forget exactly what the issue was, but there was some issue where we couldn't store an address into a dereference, which was frustrating. But now we can. So we should get 333, 5. Is there not another 5 there? I guess, yeah, 333, 5, 11, 50, 50, 57. 333, 5, 11, 50, 50, 57. Boom. That's great. We didn't really add any language features this time. Not really. Local variables didn't really matter, in my opinion. But we did generalize so much stuff that we fixed old examples, and that's good. So that's what we got. So yeah, that's all. Yeah, got any questions? All right. Let me look at the syllabus and see if there are any good optional homeworks to offer. Where is it? Syllabus. Yeah, no, not yet. I have a bunch of stuff that I want to get to, and that I wanted to get to by now, but we missed enough lectures that we're not going to get to them yet. So, looking at the schedule, we have how many weeks left? We got 4, 5, 6-ish. 5. We have might be 4 with reading week and finals week. Okay, I'm just gonna assume 4 weeks conservatively. We will get to arrays next week. Also the preprocessor. We can get to structs by the end of the semester. Here's one. You should implement the binary logical operators. So and or any other ones you want. I don't know.
Wait, the logical ones or the bitwise ones?
I think LVM does distinguish. Let me see. Bitwise binary. I mean, bitwise logical and. Implement this. I think, well.
So it doesn't have like short circuiting, I don't think.
Not LVM doesn't.
Or like if you do bitwise.
I mean, that's correct. Yeah, because it acts, you know, not as a logical operator. It's not doing logic, but yeah, just let's do logical.
Okay.
Logical operators. Don't worry about short circuiting. I bet LVM does that for us. So I don't know. I feel like short circuiting has. I don't know. I'm not gonna say anything that might be wrong. So I'll just yeah. Give me and or an XOR and not.
Just some like integers.
Say again.
Just some like integers. Like you just wanted to return an integer basically.
An I1.
Okay. Or
Because that's what we need to do branches is an I1. I mean TY. Yeah. So you can just say and I1, right? Bitwise logical and yeah, yeah. That looks right. Oh, okay. This combines both. So if you tell it to give you an I32, it's going to do that. Yeah, it's going to do the bitwise then, but if you just ask for... Oh, will it though? Let me look here. Nah, I'm going to make you look. It's your homework, not mine.
optional homework?
Optional homework, yeah, yeah. Yeah. Cool. Well, yeah. I don't know. I'm trying to think how I would implement it, but you'll figure it out if you want to do it. It'll be a nice addition to the language. So, that's it. Thank you.